done deal.
It's actually a very similar concept to this course. Not on this side of that course.
There we go. Did you guys work together?
He was trying, but I wasn't responding.
Yeah, because like I could explain all like later on.
Please do.
Yeah, I think that
I need someone to.
we can do that.
Yeah, that'd be
And
awesome.
it's just like because I did like the first two .m files, like the map loading and seeing if it collided, and like it took a bit, but I think I got them. But now I'm on like the main one, and it's like I looked at some pseudocode and some version of that. I guess sort of get the idea, but just
Okay, so yeah.
Has the due date been changed to Saturday? Because that's what it says on Canvas.
Yeah, the due date for both of your homework 0 and project 1 phase 1 has indeed been extended.
Okay.
So-
Because the PDF doesn't say that. and I
No, the
didn't see
PDF obviously has not been modified, but it has been extended as mentioned in the last lecture.
Okay.
So that's good news.
And homework 0 is extended until midnight tonight, right?
Exactly. So, if anyone has any questions regarding the homework, we can get that out of the way. Or if you want, we can start with the examples. However you would like to do that.
There's also office hours from 5 to 7 today.
Yeah. But yeah, I mean 5 to 7, if it's inconvenient for people who might have a class later on, you can use this time here to discuss further. So, okay. I think we can come back to Dijkstra if any of you want to do Dijkstra first and then A star, just let me know. Or should we do A star first?
I guess I just had a question about like between A star and Dijkstra. Like in the example we did in class, we had this notion of like the distances between them as costs,
Yeah.
right? And like when I was looking through, we don't really have that. We just have this logic grid, right?
In which case?
In our like in the Dijkstra.m file, like when we're starting to code that up,
Right.
all we really have as an input is the map. Or do we use? Do you think? I mean, I guess how do we? How would we
I mean, okay, so I was reserving this for the lecture, but let's talk about map representations, right? I mean, the idea is that what you have given to you in your map1 or map0.txt is one representation of the map, right? So as you know, Dijkstra, A star, BFS, DFS, whatever, they are all grid search algorithms, right? So the idea is that in the real world, you don't have grids, right? You have what we call a continuous space, right? So I don't decide that, okay, I am only going to be stepping on individual tiles. That's not how I walk. That's not how I move around, right? The only reason why we grid our continuous space is so that we can apply regular algorithms like A star or Dijkstra or whatever, right? So the idea is that what you have been given is basically the real world, right? The continuous space. As I was explaining last time, you have some three-dimensional cube. So what we have given to you are the bounds of this cube and how each obstacle should look like, right? So the first step that you must do is to discretize this, which means that let's say that you have an open floor, you break it up into smaller tiles, right? So that detail and that information is provided to you. So first things first, you need to break this up into smaller cubes. That is one representation, right? So instead of a 2D grid, you now have a 3D grid. So instead of individual, squares, you now have individual cubes. So that's the first step to being able to apply graph search algorithms. The second part is that you also have the boundaries, right? Like from where to where does my world, or till where to where does my obstacle exist, and how those obstacles are represented. So now that you have sort of made your world into a grid, you also need to make your obstacles into individual grids. And you obviously cannot go there So that's what the map.txt provides. So instead of providing you the locations of each and every one of the cubes that are there, we have just said that, okay, this is your world, which you know. The obstacles look like this, and you must create the discretized world yourself. That's the basic idea of the load map function. So, okay, so yeah.
What's the purpose of the colors in the box there?
The colors are just for visualization so that you can debug. And the colors are mainly used to distinguish objects like obstacles from each other.
But for the purpose of solving the question, we might not need that, right?
No. But you will need that as part of your load map, as part of your plot path or whatever. So just continue with the assumption that, yeah, it's a necessary information. Okay, so we can proceed with the old example of Dijkstra, if anyone wants that, or we can proceed to A-star. So just Dijkstra first or A-star first? Okay. So we'll go through the same map as last time. If you remember, we had a set of nodes. So these nodes, so this is a little abstract, right? You might have trouble relating to your given question. So you can think of nodes as if you have a map which you have discretized. Obviously this is in 2D. You can think of nodes as individual cells. That's one way to think about it. Obviously this example does not include the obstacles, but the concept remains the same, which means that you can either go to a node or you cannot go to a node, right? So that's how this grid translates to the problem that we will be solving. Now, since Dijkstra is a graph search algorithm, it makes more sense to represent your nodes as graphs. So that's why we are performing the example in this manner. I think this is E. Okay. So yeah, who remembers what are the relevant data structures for Dijkstra? This was not there. What are the relevant pieces of information that we require for Dijkstra?
Visited, non-visited. We make arrays which represent the visited nodes, then the non-visited nodes.
Correct. So we need two arrays, right? One visited and one non-visited. But that's not that. Like, if you remember, there was a table, right? So what are the contents of that table? Yeah, that's the first thing. I have not written those. So it's a weighted graph, right? Dijkstra doesn't work for a non-weighted graph.
Yeah, so I guess that was my question, is are our weights then just coming from our distances? Is that the idea?
Yeah, in your case, that would be the obvious value, in that your weights would be directly, I'm not saying it's going to be the exact distances, but let's say that it would be some factor of your distance.
Okay.
I mean, ideally, you would have a lot of other factors also, right? So these weights could be, as we explained, terrain values. So if you have an uphill, the value would be higher. In case of Google Maps, let's say, if you had traffic, the value would be higher. Things like that. So these weights, in your case, would be a direct proportion of your distances.
So in case of the project, the weights would be the Euclidean distance to the next node, right?
Yeah, that depends. That depends. It could be any distance measurement, right?
Okay.
But that's up to you to choose, whichever gives you the most accurate answer.
No, my question is, how do you discriminate? So if you have grids around each other, so to go from one block to the next one around it, so say I have 8 blocks around me, so to go to each one, the Euclidean distance would be the same. How do I discriminate? How do I weight appropriately?
In case of Dijkstra,
Yeah.
like this will become more clear once we start discussing the A-star problem. But in case of Dijkstra, you you don't really, it doesn't matter, right? Because you're going to be exploring all the surrounding edges.
Right.
So in case of Dijkstra, that's not a very relevant factor. You just pick. Let's say that you have ordered, it won't be, yeah, so let's say that you have ordered them according to some number, right? You go in one clockwise direction and then you pick the lowest one, let's say. That's one way to do it. And you given a cube, you will have not 8 but 26, if I'm not wrong. 20, like you can have, because you're not just counting top down, left, right, back, front. You will have diagonals also. But you can do it without diagonals, but it's going to be super inefficient. So that's again up to you. So yeah, the relevant table for this. What are the 3 pieces of information that we require to solve Dijkstra?
You just said without doing the diagonal, it's going to be super inefficient. Why is that?
Think about it this way. I'm going to do a small example in 2D. Let's say that this is where I am,
Right.
and I only choose to go in these 4 directions, right? What's going to happen is that my path, whatever I generate, will end up looking something like this, only at right angles. This is obviously not the shortest distance from here to here. It's this line right here, which means that unless I allow my robot to move not just this way, but also this way.
But in terms of A-star algorithm, like computational wise, I feel like if you only move like 6, 1, 3 directions, then you have then you can only count because you discretize with like with certain numbers uniformly, so you can
Right.
count. But when you are doing diagonal, you have to use Pythagorean theorem. You have to actually calculate.
That's right, but then that's a one-time thing, right? Your heuristic value in case of A star, you will do a 1 pass, and that's it. Because the heuristic does not change. You know your start, you have an idea of your goal. You do the, it's a grid, right? In A star, it's definitely going to be a grid-based thing. So you do a 1 pass, and we'll come to that example. There'll be a detailed example. It's going to be a 1 pass, and so you don't worry. That's like, you can think of it as O of n, right? Where n is the total number of cells or whatever.
But suppose there is an obstacle on your right. There is an obstacle up. Can you go to the upper right?
Could
I
you?
mean, if you can go diagonal.
Yeah.
If there is an obstacle on your right and there is an obstacle up.
Yeah, you can go diagonal, which means that let's say that you have a 3 cross 3, right? Let's say this, right? So you are here, you're saying that there's an obstacle here and there's an obstacle here, right? So you can go this way. Now, if you only allowed sideways movement, this would cause a severe increase in your length, right? You would have to go all the way around. So you can do this, you can do this. Is that okay? Okay.
We can only do that if the nodes are at the center of the square, right? If the edges are the nodes, then you can't do what you do.
Edges of the nodes?
Like the edges are, if the edge between
Okay, so you're saying this is the right.
like the 2 obstacles, with the point where
Yeah.
they meet, if that's the next step between here and there, then you can't do what you just did.
No,
right?
I mean, okay, so you're saying, can you,
Yeah, I can.
yeah. So you're saying this is blocked?
So if you're going from if this is your node currently and your next node is here,
Right.
then what you said works.
Right.
But if your next node is this, then you can't do this. Right?
No, you're only going from cell to cell. You can't go to.
So you're not going from edge to edge.
No.
So if you do this 3-dimensionally,
Yeah.
so you're saying you're going center of cell to center of cell.
Exactly.
But then the obstacle would be till the edge of the cell, right? So you would collide with the object halfway through. So say near the
Okay.
boundary over here. I'm just going to ask another question.
Right.
So this is the boundary.
Configuration space, right?
That's why you do the configuration spaces.
Yeah,
That
you
doesn't
treat
have-
them as
The-
point
the
objects.
margin, right?
Okay.
You can think of, because ideally your next one would be only edge to edge touching, right? Your very next obstacle would be something like this, right? It should be touching this edge, which means that you can imagine that this whole cell, this whole cube will be blocked.
So if you are here, you can't really go to that.
No, you can't. You have to go via.
Yeah,
Of
okay.
course.
Yeah,
Yeah.
that's,
No, but in 2D it
Yes,
obviously
okay,
scales
yeah,
down.
yeah.
But
that's what I was trying to ask.
so moving on. One of the data structures that you will maintain as part of while you're doing Dijkstra is the current vertex, whichever it is. You will maintain the D of A, or in this case A is your start, or whatever, whichever node you choose. And you will also maintain the previous vertex list. So this is the data structure that you will require, along with your two lists of visited and not visited. So let's maintain that. So visited currently will be empty, and non-visited currently will have your list of all the nodes, right? So A, B, C, D, E. Okay, so what next?
What do you recommend as a priority queue in MATLAB? Because it doesn't really.
Keep a dictionary. So a dictionary is a key value pair, and you can sort according to that. So it's basically a int of int, right? Or whatever.
Does MATLAB have?
I think, I'm not exactly sure, but I think MATLAB might have an inbuilt priority queue, but it's not like, you don't have to worry too much about it. You can just say that you have a key value pair, right? So what you can say is, if your key is A, let's say that you give it the highest priority of 5. So this priority will be an inverse of the current value, right? Because you want the smallest value to move to the next one. So the smaller the value, the higher the priority. So that's how you will organize your data structure. Did that make sense? Sort of?
Sort of.
Okay, let's proceed with the example. I'll come back to this. So the first thing to do is that we know that we're starting from A, right? So what's the first step here?
Put A for our first vertex, that distance would be 0.
Right. And
There's no previous. Yeah,
so
it's
this is a null
an
value,
A.
right? Now what? We are at A.
You can move to B or D.
Right. So the correct algorithm is that we take the adjacent, immediate next neighboring values. So and then we put A here, right? Because we are done with A. So now we are at B, right? So let's put all of them down. Okay. So what's the value for B? Now what? So in case I missed out last time, to actually implement this, you need to set the initial values for everything to super high, right? So this will also be infinity, but 0 is obviously smaller than infinity, so that goes in. So whatever. So next we come to B, right? So what do we do?
D will become 6.
Right. So the value for going from A to B is now 6.
The previous vertex will become A.
Right. We can. That's fine, right?
No, first then we'll visit D and then we'll come back to B.
Okay. So now we visit D.
D.
Okay. So what's at D?
D is 2 and the previous vertex is again
So this is 2, this is A. Okay. So now what?
A. Now because the D value is less, so we first visit D.
Correct. So you have to keep popping from this list, which means that what's next?
Now D will pop.
Correct. So this,
So this algorithm can never backtrack. That's the idea.
yeah. It's
like what if you, I guess it's not really possible for it to get stuck then, right? Like if it hits some kind of wall where it can't move.
Yeah, you can't, you just have to skip those nodes. So the idea is that these are all the nodes that you can visit. You're not exactly taking into account obstacles here. That obstacle basically, the idea of the obstacle is either encoded, it's usually encoded in these weights, right? So let's say that you had an obstacle F here, this would have a very high cost. That's how you take care of obstacles when you're doing Dijkstra, is that you cannot visit that. That has a movement cost of infinity.
Okay.
So that's one way to deal with obstacles. Okay, so now what?
Now from D we can move to B and E. So we first see B.
Right. So why do we see B? Because it's not yet in the visited list. If it was, we wouldn't. Okay, so from D we check B, right? So what's
So now it will be 2 plus 2, that will be 4. The DA will be 4 for B.
so this gets updated to 4.
And we get to D.
So
Then we visit E. E is
we
3.
visit E. E is
3.
3. So why 3?
2 plus 1.
Right. So you always measure it from
A.
the start node, whatever you picked. So this is
2
3,
plus 1. Yeah,
and the previous node is
D.
D.
3. Then we visit E because it has
so
numbers.
you
So now
put-
we pop E.
Okay. So you pop E, right? Okay.
Again visit B.
Do you have a
I have a question. So you changed when you were going from A to B versus A to D, you changed your visited and not visited list?
Yeah. So as and when you're done with a node, which means that you have explored all of its neighboring variables, you can remove them from the not visited to the visited, which means that you're done with these 3 nodes. You don't need to look at them again.
So like B, we have a path from A to B that still has unexplored options.
A to B?
Like you have A to B,
Yeah, A to D, there is only one way to go, right?
well, from A to B, we could do like A to B to C. We haven't explored that yet. So,
Okay. I didn't get you. You want to go from where to where?
so we started, the first step we looked at was A to B,
Right.
and then B was on the visited list.
No, that was a mistake. He
Oh.
corrected.
Oh.
So you can still see that B is not removed until you have explored all possible options for B, right? Have you explored all possible options for B? No, right? So it's still here. Okay. So next,
But did we explore all possible options for E? Can't we go to A to B to C?
no, what I mean is we have explored all possible options to get from A to E, right? We have the minimum cost, which is that from A, if I want to get to E, I will go via D with the cost of 3. That's what that means. So
But you also have the A, B to E that we haven't calculated yet. That could
yeah,
be-
but if you remember A to B to E, we already updated the best way to get from A to E. From A to B. To get from A to B, we are not going to go like this. We are going to go like this. Which means that this path, which is from A to E via B, is automatically eliminated, right?
Okay.
Because we have updated this guy right here.
But it's only because that A to B has a high cost. It's not
Exactly.
necessarily-
It's all ordered by cost. That's the priority queue that we are looking at. Okay, so next, where are we? So this is the priority queue, right? Which means that what's next on the list? You sort them initially by whatever value, and initially they don't have a priority, but then now based on your scores, they do have a priority, which means that currently you're done with D, you're done with E.
No, we have just popped.
I mean, what I mean is now we're proceeding with the next iteration, which means that we can see that A is done, D is done, E is done, right? What's your current score for, so now you see B, okay? What's your current score for B? 4. What's your current score for C? infinity, which means that according to your priority, you will pick B. That's what it means. So coming back to your question, you will maintain this queue where you will have a k key value pair, right? Something that looks like this. So each of your keys will be each of your nodes. So A, doesn't matter, but we'll put it there. So right now it's 0. And you will, so what you can do is, okay, I shouldn't be telling you this, but you can have one node struct, right? If you guys are familiar with structures, you can have one struct for a node, and each of them will contain all of the important information that you need. And you will have 2 separate lists for visited and non-visited, each of which will contain one of those node structs. So same for B, right? What's the current value for B? 4. And then you sort this struct array. It's an array of structs, right? So you sort this struct array based on the value.
Every time?
Every time.
That's so inefficient.
Ideally, you would use a max heap or a min heap, but
MATLAB
let's
does
not.
have-
It does not have all that.
But
Yeah.
MATLAB I think MATLAB can call Java.
It can.
So
If
we
you,
can-
yeah, if you want to actually implement this, you would rather use Python or C++. But this is for people who are just getting started with coding and who are a little shaky with their basics. So who have not yet taken an algorithm and data structures
So
class.
the timing limit is pretty loose.
Timing limit is 10 times what you require.
Okay.
Just saying. It takes 3 seconds for us to run both A star and Dijkstra. You have 30 seconds each. So you have no problems with the data structure
running
part.
at 300 seconds, then you should.
Yeah. Yeah. If it goes, if you are reaching within delta 1 second of the timing limit, you should be worried. There is something drastically wrong with your code. Just keep that in mind. It should not take you more than 10 seconds to run the example that we have given you. Okay.
Hey, so why isn't the cost from, because now that we're at E, right? So
No, we have popped E. We are done with E. We are moving on.
but
We
so
come back
we
to
pop it when we get to it though, right?
no. It means that we are done visiting E. It means that we have looked at E. We have taken into account all of the costs.
So we're not like making the path yet.
No. The path will come from this table. The path will come from this table. Right now you are exploring the whole map or the graph given to you. The path will come once this table is completely finished. Once your non-visited list is empty. That's when you know your algorithm has completed. Okay, so anyone? Okay. So what's next?
We calculated distance
We-
from E to B. And
Yeah.
We have not done that.
Okay, so this will update, right?
From E to B.
From E to B, which means that we have to pick B now. We have, like, we are going
We have not
to,
explored all the nodes connected to E yet.
we have not explored all the nodes connected to E yet. So E still remains here. Okay. Now
Now pick E.
okay, we pick E. Then what are
We can't visit D, we'll be visiting B and C.
okay? So
So
what are the
visit
corresponding
B,
values?
it has a value of 5, which is higher than the already existing value
Correct.
of B.
So we don't update it, right? So this stays as it is. C.
plus
What's
8.
So this goes to 8 and
E.
previous value becomes E. So now we are done with E. Then that goes here and that goes out.
We pop B to E.
Just to prove we are done with one iteration, we update the key value pair in our priority queue. Now remember, this is always sorted, so that's fine.
Wait, where do we get E from?
8 because you look at your previous values, right? So we are going from A to E, A to C via E. So 2 plus 3 plus 5. That's 8.
Oh, okay.
Yeah. Okay.
plus 3 plus 5 is not 8 plus 4.
Whatever, my bad. 5 plus 3 is 8. Okay, next.
B has the least value.
Okay, so we look through our queue. B has, so D we can successfully eliminate, and E we can successfully eliminate. So this is our queue, and each of them has a flag, right? So let's say that currently A, D, E has flags of 0, which means that we are done. These ones still have a flag of 1, which means we are not done. So given this, sort by key value and then you come to B, right? So B, now what?
You can only visit C, we see the value is 9, you don't update C.
Right. So this is done, this is done, this is done. So the only value is 9 from B to C, and obviously that's greater than our current value, so we don't bother with it. So we can also pop B. Okay. Obviously we change this, so we are left only with C. So there's nothing for C, so that remains as it is. So now that your NV is equal to the null set, or whatever, it's empty, you know that you're completed with your algorithm. This table now gives us so this table now gives us the completed planned path, right, from any node to any node. But the idea is that you want to go from, let's say, A to C, right? So how will you go from A to C? You come to A. Here you check the next value, which is A, right? So from A you go to D via A, which is obvious. Now that you're at D, you can go to E, right? Oh, I haven't updated. Yeah. So you go to E with a score of 3, cumulative, obviously. So 2 plus 1, 3. And you go to C from there with a score of 8. So which means that this not only gives you the cost to go from A to wherever, but it also gives you the path of how to go. Because you have the current node, you have the previous node, and you sort of link them together. So the way to find your path is to sort of backtrack, which means that you go from where you want to go to where you are. Is that concept clear? We backtrack. You pick the node where you want to go, let's say C, and you pick the node where you start from, and then you keep checking the previous nodes until you get there. So E, the previous node is D. From D, the previous node is B, and from
D, the previous
is A, whatever. So you get the idea. Yeah. And then you just keep backtracking till you reach your start node. So
now we know you named the nodes A, B, C, D. How do we actually do that? Like with the current grade?
call it whatever you want. I mean, no one cares, right?
State and name.
Ideally, it would be IDs. You have a big cube, you have divided it up into smaller cubes, which means that each of them has a 3D location, right? I can call 1, 5, 3 as A, doesn't matter. So that's how you would proceed with your example.
So what happens when DA value is equal for two nodes?
When this value is equal for 2 nodes, right? Just pick the first one.
Okay.
Doesn't matter.
So would that have some consequences over the further exploration?
Not really. I mean, think about it, right? You have in Dijkstra explored every node, right? So it doesn't matter whether I take this first or I take this first. It really doesn't matter in your final table. You will still get the correct output. So you can change these values and try it out for cases where the values are equal. It won't matter. So what you can do is you can take you don't have labels, right, in your case. So what you can do is, let's say that you take the x value, the least x value, and pick that first or something. I mean, it doesn't matter, up to you. That's one way to break these ties. That's a good question actually. So I hope that part's clear. Okay, we are good with Dijkstra. Obviously this is in 2D, but the algorithm remains exactly the same and you can scale it up to 3D. We now come to a slightly more involved example of A star. Okay, before we do that, what is one of the obvious disadvantages of using Dijkstra? Correct. So we want to use a more focused searching plan, right? We don't want to explore everything. Obviously this has like 6 nodes, 5 nodes, it doesn't matter. But in your case, you have a very large number of nodes. And it's obviously, Dijkstra will take some time to explore everything. So we come to the example of.
But if we know the end node in this Dijkstra algorithm, as soon as that end node comes to a visited list, we can stop the algorithm there itself.
Of course, but you are not guaranteed a shortest path in that case. Think about it. If you haven't explored all nodes, you are not guaranteed that there is no other path to get there, right?
No, if we have already taken from the non-visited list to the visited list, that end node, I'm not saying that when we have visited, considered it, like when we were doing it, from when A was moved to visited, we had already seen the path to B and D.
Right.
That did not confirm that the shortest path from A to B is given. But when we popped out B from the non-visited list to the visited list,
right,
now it was confirmed that the path from any other node to B is
correct.
From our starting node,
right.
A to B is the shortest one.
But think about it, the list that you're creating, right? You need to order it in that way, right? So that so what you're saying, like you stop when you pop the so-called end goal, that would anyway happen, right? Because that is usually the last thing to visit anyway. You're not going to be, that's one thing, you're not going to be putting everything in your list. So that's what we had sort of talked about, that you only discretize what you need, so that you're limiting your search space. So as and when you come to a particular point, you discretize, let's say, 26 other cubes around it or within that neighborhood. And then once you get to a new point, you discretize again, so on and so forth, which means that your non-visited list will not be 10 to the power 5, which is, let's say, after you've discretized, you don't need that many values, right? Because most of the place will be free. You don't need to talk about them. So that's one way to reduce your search complexity and increase your computation time. Does that make sense now, what we explained last time after we have done this example? Let's say that this graph that you have taken, that we just showed, is only a subset of everything. We don't need to consider everything. We can only take the subset that is currently relevant to us, work around it, work with it, and leave out the rest of the stuff. That will greatly improve your algorithm time. And if you can do that, it will be clear in your execution timings. So let's move on to a quick example where we talk about A star, right? A star is a little more involved because there are certain hacks that you do to improve Dijkstra such that you don't have to explore everything, right? We focus our search only between our start and our end goals, right? Let's say that this is your graph, right? This is the place or the world that we must explore. They are ordered, they are each given a particular ID. Now this ID in this case is one-dimensional ID, but you can also specify a particular location by their x comma y or x comma y comma z value. The blue is the start and the red is the goal, right? So we must get from 7 to 24. Here again we have certain data structures, One of them is obviously how do we represent a node, right? In case of A star, each node has a set of 4 values, right? One of them is the H value, which is the so-called heuristic value. We have the G value, which is the movement cost. We have the F value, which is the sum of the heuristic and the movement cost. And we have a parent, which itself refers to a particular node. So that's how you represent each node, as I said, using a struct or whatever. And we have 2 lists, which are the open lists and the closed list. With that in mind, let's move on to how do we calculate the heuristic, right? The heuristic is basically a sense of how far away we are, not exact terms, but sort of a guesswork on how far away we are from our current location to the goal location, right? Now, obviously, you can use multiple distance measurements for that, but in this case, let's say that we are using the Manhattan distance, right? So from 7 to 24, how many squares do we have to move to get there, right? So 1, 2, 3, 4, 5, 5. In this case, the heuristic value for 7 is, let's say, 5. In case of node number, let's say 16, how many squares do you have to move? 4. 1, 2, 3, 4. You don't count that node, you count from the next node.
So can we not do diagonally in this one?
You can. That's when you take the Euclidean distance, right? You can literally, as I was mentioning last time, you can literally put a tape measure here and a tape measure here, and then you can take that. It's a heuristic. It's not an exact value. It's just a sense of how far away you are, right? In case of Dijkstra, we had no idea if we were near the goal or if we were close to the goal or whatever. This gives us a direction in which to move. So that's where the heuristic guides your searching. So that's how we compute the heuristic values, right? I have populated, in this case, with orange, all of the heuristic values or the H values for each of the nodes. So for node number 1, that value is 7. For node 2, it's 6, 3, 5, so on and so forth. If you will notice, the blue ones are the obstacles, and we haven't taken into account their heuristic cost because it doesn't matter. And because this is not an exact value, you will notice that in case of node 16, let's say, I have just crossed over the obstacle. It doesn't matter. But you do count that as one distance. It's not going, obviously, when you actually start searching, you will find that you can't go through an obstacle. But for our heuristic, which is just a guesswork, we take that as a normal square. So these are the heuristic values, right? Let's now compute the second part of our node data, which is the movement cost, right? So the movement cost is basically, for that node, is the G value, movement cost of the parent, plus its own movement cost to another node, right? So this is where, as he was mentioning, this is where your Pythagoras thing comes in. Let us say, so you will see that I have given a certain cost to move vertically or horizontally, and I have given a different cost to move diagonally, right? So how do we get that value? It's a simple estimate, which is that, let's say that I have a unit cube of 1 and 1. So what is this root 2, which is 1.41, whatever. Forward. So I just multiply them by 10. That's how I get my movement costs. Obviously, in a real world example, these movement costs will be far more involved and will have a lot more variables which decide the cost for moving, right? But in this case, that's how we weight them. Any questions regarding how we reached here? Okay. Now we come to the open and closed list, right? We know our start, which is node number 7, right? Once we come to node number 7, let me draw that here. I am here at node number 7, right? What is the heuristic cost for node number 7? 5. We have these two values. we have other squares around it like this, we are here, right? Now what we do is, what are the immediate neighbors of node number 7? Right, so 1, 2, 3, 4, 5, 6, 7, 8, 11, 12, 13, right? So given that I'm here, all of these surrounding nodes get into my open list, right? Which means that they are under consideration currently. And because I am at 7, I can put that 7 into my closed list. If you will notice, 8 does not factor into your computation at all. Now we can start updating the movement costs, right? So I was here, to move here, that's 10, right? To move here, that's 14, 14, 10, 10, 14, 10, 14, right? So those are the values that you see there in blue, right? Those are my movement costs from my 7 to my other nodes. Now one thing that you must note is that once I am at 7, I set all of these neighboring nodes as having parent as 7, which means that you can think of them as having arrows, right? You can think of them as arrows, all of which point to 7, right? Which means that if you remember, my node had one field which was parent, right? In the node data. So in this case, the parent is node 7. And I have my heuristic cost. Now we remember again that f, the final cost, is equal to the heuristic plus the movement cost, right? So that's the green one, right? Which means that I am at A, so my movement cost is 0 because I am already at A. So movement cost of the parent plus my own movement cost, right? Which means that 7 plus 14 plus 0, which is 21. That's my final cost. That's my F value. Same goes for 2, which is 16, 19, 16, nothing there. 8 is an obstacle, 19, 14, and 17, right? So that's the green value. So you have F equal to G plus H. Any questions?
Can you say that again?
Okay, so if you remember our formula, it was F equal to G plus H, right? Which is the movement cost plus the heuristic cost. So what was the heuristic cost for 1? Can someone? 7. 2. 6. 3.
5.
5. This one? 6.
5.
5. This one? 0. This one?
5.
5. Okay, this one?
4.
4.
3.
3. So we now sum these values, right? We now sum these values. This one is obviously, forget it. So once we start summing these values, what is the F cost for this node? 21. What is the F cost for this node? 16. What is the F cost for this one? 19. 16. Doesn't matter. Doesn't matter. 19, 14, and 17, right? That's the ones that are mentioned in green. Now, again, here we come to the priority queue idea. Again, we revisit that, which is that every node struct can now again be thought of as a key value pair, where your key is the node ID and your value is the F value, and you sort according to that, which now gives us a way of moving, right? So right now, based on your current location 7, where would you move next? You would move to 12 because that has an F value of 14. 13, because it's a diagonal, has a slightly longer distance. So that's why it's 14, right? I mean, even though it seems like a good way to go, which is like visually speaking, you can just keep going diagonally and come to the start. But we have decided to set our movement cost such that we are favoring vertical movements over diagonal movements. So that's one factor. That's why the next list, the next node we move to is 4, right? That's my next point. We have now moved 12 into our closed list, and we have removed that from our open list, right? So before we proceed, what we have is we have this little slightly messy but pretty intuitive update rule, right? So how are we updating our lists at each iteration? So now, if you will remember, we have reached 12, right? We are currently here. The parents remain the same, right? We don't update the parents for each node. What we do is, now that we're here, we check our adjacent lists, right? We see that surrounding 12, we have 6, 7, 8, 11, 12, 13, 16, 17, 18, etc. We know that 12 is currently parented to 7, right? If the G cost, so now that you come here, you will again do the same computation for each of these values again, right? We now check the G cost for the previously parented node. If after coming here the G cost is lesser, then we update that parent, which means that, like, this is, like, obviously that's not going to happen now, but this is what will happen. We switch parents. And by looking at the arrow at the end of your complete computation, what you will notice is that the arrows will sort of point you from one node to another. So again, similar to what we did with Dijkstra, you will have a list of vertices and their parents, right? So after you're done with this list, once you're done going from start to goal, what you can do is you can just keep looking at your parents. Given an end goal, you start looking at its parent, you move up. Looking at its parent, you move up, so on and so forth, till you reach your required vertex. So that's where this parenting comes in, because in case of Dijkstra, we were doing the previous vertex, right? But that was obviously inefficient, and now that we are not exploring all the vertices, we have to maintain a list of where we came from, which is the parent. So similarly, yeah.
How would the G cost change? So you're doing a movement from one node to the other, checking the G cost and moving back to your parent node?
Yeah, I mean, so if you remember that the G cost is the actual G cost is the cost to go to the node, which means that when you're here, you spend some value coming here, right? Plus the G cost of your parent node. In this case, what is the value?
0.
No, the G cost.
For the parent node?
Yeah, it's 0 plus, you came here, right?
Plus
10, yeah, plus 10.
Plus another 10?
Yeah, you have to consider that once you switch to a new node, your parents don't change, which means that the parent for this still remains this one currently. But if, let's say, that the G cost after I have moved is lesser than my previous one, then I update my parents, right?
How is that possible? So you're only adding a value to it. How could it ever be less? If you have the cost of moving plus a new cost of moving, how would you ever get a less?
Okay, I have to modify the numbers to do that, but there is, okay. So let's say that you have here 5 and 5, 10. Here, once you get here, this is also 10. So there is no change. So you don't have to update. In this example, it's not very clear, but I can send you guys an example where this will make more sense. I mean, I have to do the math and get you the correct answer, but I have an example where updating the, you need to update parents, right? So I mean, think about it. What does the parent do? Because what you have here are other nodes as well, right? You also have these nodes, which we aren't taking into account. We aren't completing the calculation. But the idea is that from here, let's say to go somewhere here, right? Okay, so I think this might be clear. I'm just going to name them randomly, 14, 15, 16. We have the heuristic cause, whatever, right? What this means is that initially, my parent for 12 was 7, right? And I had a G cost here. Now, once I am here, let's say that moving here to 15 has a lesser G cost than moving from 7 to 12, right? So then, automatically, this 7 is no longer my parent, right? I have to update that to make 15 the parent of 12. That's what it means. So ideally what will happen is, once you are done, so these will all get parented to, these will all get parented to 12, right, as you expand. But it might be necessary for you to change one of these parents to say that, okay, instead of parenting to 12, instead of parenting to 7, it might parent to 13. And that will change the path that you take to go from your start to goal. I'm sorry I didn't get that concrete example, but I'll send you a link which will clarify the whole problem.
Yeah, that's more clear.
Yeah. But the idea is that this is not complete, right? So when you reach 12, you populate the next set. So this again comes into your dynamic or on-demand discretization, which means that initially I was only considering this grid, right? I was here, I was only looking at this surrounding part. As I moved, I discretized further. Now once I come to 13, I can discretize further, so on and so forth, which means that this map is only a subset of my complete map. So that's one way you can reduce your computation when you're doing Dijkstra or when you're doing A star. So yeah, in case of Dijkstra, actually I don't think that will work because you have to explore every possible node. But in case of A star, definitely that's one way to proceed, is that you only discretize when you get there and update your values accordingly. Okay, so that's the quick example of Dijkstra and A star. If you have any queries, we have like another 15 minutes. If you have any queries regarding any of the projects or the homework, you can ask now. Anyone facing any particular issues with any of the functions?
Did anybody try submitting and try the leaderboard?
No, that's not working.
Never mind.
That's not yet functional. I mean, you can still submit, but the grading won't happen.
So how frequently is the grading happen?
Hopefully every like 15-20 minutes. Yeah. I mean, you only get 5 tries, so you shouldn't use up all your 5 tries in like an hour. That would be pretty useless.
You can use one.
I mean,
There are limits for the server?
yeah.
So you can only submit 5 times and you take the highest?
Yeah. We will take the best score.
Is it graded by hand?
Huh?
Is it going to be graded by hand?
No.
No.
That's why the submit server. We have a script that will go
Just
through.
offload this pass.
You can dispute the graph and show it. Sure. You don't think we'll look at it at all?
Yeah. I mean, part of it will be graded by hand, right? Your plot path, for example, will definitely be graded by hand. We will be testing it on 2 different or 3 different maps that we have separately and check it on that basis.
And if your code is running at 0.5 seconds, then we'll definitely.
I mean, if it runs on whatever laptop or whatever in a certain amount of time, just assume that it will run at, let's say, half the time, yeah, on our systems. What's the progress?
There's a problem regarding downloading that 17 software. It's showing the error message.
What can you
It just says
further detail?
I just go to the software site. I try to download it. Just says there's an error.
Are you installing on Windows?
Yeah.
Okay, you have to figure it out yourself. Windows help will not be provided. I mean, one of the things that can be happening is that, are you connected to the internet?
Yes.
You're sure about that?
Yes.
Okay. Because that's one thing, when you install it, has licensing issues. Another thing, are you installing it from home?
Yeah.
That might be an issue. Try connecting to the UMD network.
I installed it from.
You install from home, it's okay? Okay. You are on Windows?
I mean, I just clicked on the link and installed it.
And then we 24 basically that's the first key, right? That they're giving out.
Yeah,
I'm
you.
not saying download the MATLAB. I'm saying download the key from the software you
Oh no, I
Yeah, the-
already had a license.
Okay, so one thing is Topware does not give you the key.
It gives the key.
You have to log into MathWorks, sign up, and then you will get the key.
No, that key is for 30-day trial. When you go to Topware, they say that they give you a key which you can input and then you can use it.
Then
License file you're talking about.
no, the key. The student version works differently.
I just signed in with my MathWorks account. That already had a license.
So one thing you can do is, instead of putting in the key, they give you an option when you install MATLAB to log in, to connect using the internet. You sign in and that works. So there is no key to be put in that case, I believe.
No, they ask for a license.
They
but
still ask you for-
But because we are students, they give us 30-day trial period.
That's not how it's supposed to work. You're supposed to get complete unrestricted access to MATLAB. There is no trial involved.
For that, all these
Okay. Anything further?
Come off this hour, we'll try to figure that out. There were a few people who said they were not available at all for either of the 2-day office hour. Is that because you don't prefer, or is that because you have other conflicts?